My name is Sylvia Leon, and I am going to talk about a relation of cyclopentanones by palladium and enamine cooperative catalysis. This is the reaction for step A and step B. We're going to start with a secondary amine and a palladium catalyst. An enamine and a XPD aryl species can be formed with a cyclopentanone in the aryl halide. For step C and D, the carbon-hydrogen metallation of the enamine will afford an enamino aryl palladium intermediate. For step E, this step can undergo reductive elimination and hydrolysis to provide the arylated ketone and to regenerate the catalyst. Also, this strategy avoids strong acids or bases, and in addition, over-arylation can be minimized because enamine formation is highly sensitive to the sterics of the ketone substrate. And furthermore, because of the redox neutral and mild pH conditions, high chemoselectivity and broad function groups tolerance are expected. In this slide, I'm going to explain what a relation of cyclopentanones are, and a relation is the process in which an aryl group is attached to a functional group or a substituent. A cyclopentanone is a cyclic ketone that consists of cyclopentane. It is used as a chemical intermediate and in making pharmaceuticals, insecticides, and rubber products. Palladium and enamine cooperative reactions. Palladium is a catalyst and is applied in reduction of alkenes and alkynes with a hydrogen. Palladium is a carbon covalent bond. And for enamines is a nucleophilic in alkylation and is equivalent to the carbon atom of the original carbonyl compound. For scale and optimization, how large of a scale can this reaction be run safely? This reaction can be run safely as long as we follow the next methods, which is, they are a hazard analysis and risk assessment is carried out in regard to each chemical. Then we also have proper training in experimental organic chemistry. Standard procedures must be applied when working with hazardous materials, and all of this information can be found in the manual Prudent Practices in the Laboratory in the chapter 4. This lab is not expensive. The materials they have a very accessible price. For the checking process, not really. Besides all of the pictures, the photos were provided by and approved by the checkers. For reaction apparatus, we have a 325 milliliters heavy wall pressure vessel and is equipped with a Teflon bushing and sealed with Teflon tape. In the first image A, we have it when we are blowing the vessel with argon gas. For picture B, bubbling the solution with argon gas, and for picture C, after inserting the vessel into an oil bath. So that's the picture. For the procedure, we have as I mentioned before, a 325 milliliters of a heavy wall pressure vessel, which is equipped with a Teflon coated magnetic stir bar, and charged with a cyclopentanone, 1.68 grams. We also added a 4 bromo acetophenone, 5.18 grams. We also added 45 milligrams of palladium acetate, 122 milligrams of triiodotoluene phosphine, and 164 grams of sodium acetate, 0.50 milliliters of pyrrolidine, 1,1,3,3 tetramethylbutylamine added with a 1 milliliter disposable syringe, a 1,4 dioxane added with a 64 milliliters disposable syringe, and the atmosphere in vessel is replaced by flowing argon into the vessel at a flow rate of 7,000 milliliters for 30 seconds, which I mentioned it in the picture before. Also, argon gas, 260 milliliters, is bubbled through solution with a syringe needle for 20 minutes. Next is the vessel is capped with a Teflon bushing, and the vessel is sealed with a Teflon tape. The reagents and starting materials was a heavy well pressure vessel, cyclopentanone, 4, bromo acetophenone, palladium acetate, a triiodotoluene phosphine, a sodium acetate, pyrrolidine, 1,1,3,3 tetramethylbutylamine, a 1,4 dioxane, a 1,4 dioxane anhydrous, silica gel, ethyl acetate, dichloromethane, and a column chromatography. In this slide, we have the reaction workup. For 1, the mixture is stirred at 130 Celsius degrees, which is the oil bath. For the next step, the color of solution changes from yellow to red in 15 minutes and dark brown in 24 hours at 130 Celsius degrees. Then after the reaction is cooled to a room temperature and is checked by TLC. This mixture is filtered through a short pad of silica gel and elute with ethyl acetate into a 1 liter round bottom flask. The resulting solution is concentrated by rotary evaporation under reduced pressure to afford the crude product as dark red oil. In this part, the crude oil is dissolved in dichloromethane and loaded on a flash column chromatography on silica gel, 125 grams. The next step, we use ethyl acetate and hexane as eluent. These products are contained in fractions of 12 to 16, and the combination and concentration by rotary evaporation under reduced pressure. This is to convert to yellow solid. And after, then solid is placed under a high vacuum for 70 minutes to afford a 2.73 grams of 2-acetylphenyl cyclopentane 1 on 4 as yellow solid. For purification, the reaction progress was monitored by TLC analysis, and as we can see, is visualized by 254 UV light. The starting materials 1 and 2 are visible from the left to right. Co-spot of starting materials in the reaction mixture, and in the slide B, we have anisaldehyde stain visible. The characterization and proof of purity. We did a TCL of column chromatography, and it's visualized by 254 UV light as mentioned before. And again, we see a anisaldehyde stain. For safety note and hazard warnings, only if person knows proper training in experimental organic chemistry, only if you know all of this training, if you have the training, then you can continue and proceed with the lab. Also, all hazardous materials should be handled using the standard procedures for work with chemicals described in references such as prudence practices in the laboratory. Risk assessments should be carried out before performing a reaction. In the discussion section, ketone moieties are found in many functional organic compounds and are frequently used as handles to install additional functional groups. Among the different ketones, functionalization procedures, Buchwald, Hartwig, Mura, the BHM arylation has been a popular method for arylation of ketones via transition metal catalyzed cross-coupling with aryl halides. As demonstrated in this research, the reaction works effectively on a gram scale. On a gram scale, 1 mole percent palladium loading is usually adequate. Although larger catalyst loading, higher reaction temperature, and longer reaction time all contribute to boost the conservation of this process. Some of the products in the scoop table have low UV absorption, which can make TLC analysis of the reaction difficult. The use of phosphomolypidic acid stain is indicated in these circumstances. As list, we have the authors. We have Yaibing Chu was born in province of China in 1995, and he graduated from Peking University in 2017 with a bachelor's in chemistry. Arjuna Prasad was born in Chicago's South Side in 2003, and he's a current student. He's a sophomore of Tulane University, and he's majoring in chemistry. The next one is Wangbin Dong was born in province in China as well in 1981, and he received his bachelor's degree from Peking University in 2003 and completed his PhD in chemistry from Stanford. Jai Jong Han was born in Tokyo, Japan, and he graduated from the University of Tokyo in 2022 with a bachelor's in pharmaceutical science. Last but not least, we have Masanori Nagatomo completed his PhD at the University of Tokyo as well in 2012.